So thank you for the introduction. So following Martin, as one of the fake organizers, I'd like to thank the real organizers for the invitation, in particular Carlo for his excellent job in organizing this wonderful workshop. So grazie mille, grazie infinite. Okay, so some time ago, I heard a rumor that I would be quit working on string field theory, and instead I would be working on the ADS-TOT correspondence. I don't know the precise source of the rumor, but there seems to be a fundamental misunderstanding. Okay, so working on the ADS-TOT correspondence does not imply not working on string field theory, as you will see in my talk. Okay, so let me start with the introduction. So one of the most important problems in theoretical physics is to formulate quantum gravity in a consistent manner. So for the computation of general relativity in the framework of quantum field theory turned out to be difficult, it was found string theory consistently describes on-shell scattering amplitudes involving gravitons. However, string theory only provides a perturbative definition of such on-shell scattering amplitudes with respect to the string coupling constant. So one possible approach to a non-perturbative formulation of string theory would be to introduce a space-time field for each oscillation mode of the string and construct an action of those string space-time fields. The resulting theory in this approach is called string field theory. I don't think I need to explain this in this conference, but okay. But since gravitons are described as states of the closed string, so natural approach to quantum gravity would be to construct closed string field theory. For closed bosonic string field theory, the gauge invariance of the classical action turned out to be anomalous, so we need a quantum correction to the action at each loop order to recover the gauge invariance. But still, existence of such formulation, closed string field theory, is useful when we handle phenomena such as vacuum shift and mass renormalization, even in the perturbative string theory. For example, you can see the nice review by Harold Ashok and others. However, formulating closed string field theory at the quantum level non-perturbatively by the path integral does not seem to be promising because of these quantum correction to the action. So as the origin of the quantum correction is related to the decomposition of the moduli space of Riemann surfaces, so I don't expect any improvement of the situation in the generalization to the closed superstring field theory. So then how should we formulate string theory non-perturbatively? So the typical origin of string perturbation theory is a 1/, expansion of the gauge series with n by n matrix degrees of freedom. So the long history of research on string theory indicates that string theory can be defined non-perturbatively in terms of such gauge theory, following this remarkable insight by Tufut. So I'm going to ask 5 questions in my talk and answer them. So if you know the answer before I do. So question number 1, what kind of cross-string theory should we consider? So while the 1/1 expansion in the gauge series has the structure of the genus expansion in string theory, we don't see the smooth worldsheet picture in Feynman diagram of the matrix fields written in the double line notation. So one attempt to generate the smooth worldsheet picture was to take the double scaling limit of matrix models. So let me draw big diagrams. So it is like, so we have, so this is the Feynman diagrams in the double line notation. So, and this can be regarded as triangulation. In the case of cubic vertex, it is a triangulation of a surface, right? So then the idea is to take the limit, particular limit called the double scaling limit of the matrix model. So then in the limit, the Feynman diagrams is many vertices dominate in the amplitude. So then you expect a smooth worldsheet picture. So this successfully defined string theory nonperturbatively. But it worked out only for low dimensions, where physical degrees of freedom gravitons are absent. Then the ADS50 correspondence can be regarded as providing a nonperturbative definition of cross-link theory in terms of a quantum field theory without containing gravity. The type 2B superstring theory on ADS5 cross S5, for example, is conjectured to be defined nonperturbatively by n equal 4 super-MUs in 4 dimensions. And the string coupling constant of the type 2B superstring theory is given by the 1 over n. So let us recall the standard explanation of this ADS30 correspondence. So when I was a postdoc at the Caltech about 20 years ago, so the Oguri-san kindly gave me one copy of this beautiful review. So let me take a look. Okay. So let's see, it was written somewhere. Okay, here. But instead of reading this, let me summarize the standard explanation. Okay. So consider the type 2B superstring on a flat spacetime in 10 dimensions in n coincident D-branes. So let me write again. So it is like we have n D-brane. So actually, this is the wrong direction. Okay. Here is the D-branes. So we have a cross-ring in the bulk, and then open string. So in the low energy region, where the energy of the system is much lower than the string scale, these cross-rings and open strings are decoupled. And in the cross-ring sector becomes a free theory in 10 dimensions, and the open string theory becomes n equal 4 super-MUs. Okay, so that was the other. Okay, this. Okay, next consider type 2B superstring theory on the 3-brane solution of the supergravity. So which is something like this. So it is okay, something like this. And then so we have crossing here, also crossing here. So because of the redshift factor, an object brought closer to this 3-brane appears to have a lower energy for the observer at infinity. And in the same low energy limit we considered before, the excitations propagating in the 10-dimensional space and the excitation around this near horizon region decoupled. And we have a free theory in 10 dimensions and type 2B superstring theory on ADS5 cross S5, which is a near horizon geometry of this 3-brane solution. Then we are led to the conjecture that this theory, n equal 4 super-MUs, and the superstring theory on the ADS5 cross S5 are equivalent. So this is what I learned from this review. So, okay, so while we are, so let's try to understand this in the context of Feynman diagrams. So while there are cross-rings and open strings in the presence of D-branes, we consider the cross-ring sector in this explanation of the ADS30 correspondence. But then its worldsheet of cross-rings contains holes. The ADS50 correspondence tells us that this cross-ring theory with holes in the worldsheet is equivalent to a cross-ring theory without holes on the curved background in the low energy region. And actually, this was discussed in the context of the large N duality of the topological string by Oguri and Buffer. So this was also this was 2002, and I was at Caltech, and I remember the Oguri-san was writing very beautiful picture, spending many hours. So this is a worldsheet with holes, And this is equivalent to the worldsheet without holes. But so actually, they try to discuss how this kind of disk appears from another phase in the IR for this worldsheet approach. Also, this was also discussed very recently using the pure spinner formalism by Nathan Berkowitz. So this is, I took one picture, the figure from his paper. So I understand this is actually this is supposed to be a hose. So, but today in this talk, I will not discuss this important problem, but instead concentrate on two other aspects. Okay, the first aspect is to see the crossing theory with holes in the worldsheet is a consistent perturbation theory. The second aspect is how such crossing theory with holes in the worldsheet can be reproduced by a theory from the open string sector. Okay, let us begin with the question of whether this crossing theory. Okay, let me write. Okay, I think I was supposed to write Feynman diagram. So this is the Feynman diagrams with holes. So I tried to write holes in a different color. I was looking for yellow chalk, but I couldn't find it. But I have blue. I think you recognize the difference. It's like, okay, green is better. Okay, maybe it's okay. So this is holes in the worldsheet. So let's discuss if this is a consistent perturbation theory. So compared with the discussion in the topological strings, I think we have to be more careful in the physical setup. So first of all, moduli space of Riemann surfaces with holes must be covered for consistency. And in the moduli space, there are regions where two boundaries are close. So sometimes also there are regions that then two boundaries are close. So such a region corresponds to a long propagation of open string. So we may naively think that the open strings are necessary for unitarity. But I'm going to claim that this is not necessarily the case because of the following arguments. First, the crossing sector is analogous to the gauge invariant sector of gauge theory. And when we consider correlation function of gauge invariant operators in gauge theory, we never see poles from fields which are not gauge invariant. So that way I don't expect any on-shape poles from open string. Second, correlation function of one cross-string vertex operator and one open string vertex operator on the disk are generally non-vanishing. Okay, let me write this down. So disks with one cross-string vertex and one open string vertex, this is generically non-vanishing. So this means that the propagation of an open string and propagation of cross strings are mixed when the interaction is turned on. So we have a cross string, but a cross string can be an open string. This is whole. And then open string can get back to the cross string, and the open string can even split, something like this. So we have this kind of propagator. So okay. So the on-shell states in this interacting theory should be identified by diagonalizing this kind of such propagators. And then long propagation of open string does not necessarily generate on-shell pole. So actually, this is similar to the situation in the mass renormalization of a cross-string theory. So if the mass is renormalized, then if you expand this way, so each term diverges when k squared is equal to m squared. But this is a fake, right? So if you sum them up, the mass is shifted. So once we convince ourselves that the degrees of freedom from open strings can be integrated out, one approach to see this cross-link theory with hold in the worldsheet is a consistent theory would be to start with the open cross-link field theory. So it is the open cross-link field theory is a consistent perturbation theory, and the gauge invariance of the action is related to the decomposition of the modular space of Riemann surfaces with punctures. But then, okay, also the Riemann surfaces can have boundaries, and we consider both bulk and boundary punctures. After integrating out the open string fields, we obtain cross-link theory with holds in the worldsheet. And when there are n consistent D branes, we write the action in terms of the Tooth coupling constant as usual. And then the coupling constant of cross-string field theory with hold in the worldsheet is given by 1 over n. So this is the perturbation theory, including gravity, that we want to reproduce by a theory without gravity. So the question number 1 was, what kind of cross-string theory should we consider? My answer is, we should consider cross-string theory with hold in the worldsheet. So I emphasize that the covering of the modular space of Riemann surfaces with hold in the worldsheet is important for consistency, for the consistent worldsheet picture. And this picture, worldsheet picture, we have this picture for any number of holds. So it doesn't have to be a lot of holds, right? So this should be contrasted with the worldsheet picture I wrote before from the double scaling limit of the matrix models. Okay, so I want to reproduce this theory from gauge theory, but then it will be difficult to see this worldsheet picture in n equal 4 super mu theory, because it is a theory after taking the low energy limit. So before taking the limit, the dynamics on the D brane is described by open string field theory. In open string field theory, it will be more promising to see this worldsheet picture. So the question number 2, what quantities should we consider in open string field theory? So in the context of ADS-theoretic correspondence, we consider correlation function of gauge invariant operators n equal 4 super mu theory. In string field theory, it is in general difficult to construct gauge invariant operators. It is in fact an important feature. I think it is an important feature of string field theory, and it is part of the reason that interacting string field theories is believed to be unique up to field redefinition given the free theory. So in the ordinary gauge theory, you can add like a trace f to the fourth. It is gauge invariant by itself, but we cannot do that in the string field theory. And in open bosonic string field theory with the cubic interaction in terms of the star product, Witten's usual cubic string field theory, there are a class of gauge invariant operators, and we can define one gauge invariant operator for each on-shell cross-link state, vertex operator, discussed by Hashimoto Izaki and Gaioto recently about 20 years ago. Okay, so these gauge invariant operators have been mainly discussed in the context of the classical theory. And they were evaluated for a classical solution to extract information on the boundary conformal field theory corresponding to the classical action. So I just mentioned 2 references, one by Elwood, the other one is a good Macaferri and Schnabel have the boundary set construction from these operators, and gauge invariant operators. But in that context, they were called gauge invariant observables, gauge invariant overlaps, LD invariants, and so on. But I would call them gauge invariant operators as we consider in the context, as I would consider them in the content context. So correlation function of LD invariants doesn't seem to be a nice way of saying. Okay, so this is the 3rd day of the conference. But has anyone explained the definition of the star product? So I think this nobody has explained. But I was a little bit more surprised. But even the definition of LD invariance. So LD invariance have appeared many times in the previous talks, but no one has ever given a definition. So, but in this talk it is important. So let me explain a little bit about the definition of the this gauge invariant operator. So let me first start with the action. The action is this way. So this is a cubic action. Inside the open string field, and the Q is a velocity operator. So let me first explain the definition of the Vezina product. Okay, it is defined by two open string states, and the open string state can be prepared by path integral over this region with corresponding vertex operator inserted at the origin. Then so this is two conformal transformation. This one maps this region to this region, and then the H2 maps this region to this region. And then Vezina product is defined by two-point function on this upper half plane. Similarly, the star product is defined in almost the same way. So this guy is defined by, so we prepare each state in the local coordinates, and this F1, F2, F3 maps this region to this region, this region to this region, this region to this region. Okay. So the gauge invariant operator, as I mentioned, is defined. It's kind of like a one-point vertex in terms of the open string. So I prepare the open string state this way. Now this map, Fi, maps this region to the whole upper plane. So left hand, this left half of the string is mapped to this line, and the right half of the string is also mapped to this line. So it is glued. So this conformal transformation is associated with the so-called identity string field. But in addition, I'm going to insert the on-shell vertex operator of cross string at the open string midpoint, which is mapped to here, red dot. So I think this is precise definition, so I wrote it. But I think it's more useful to have a more. Yes. Single trace operator. That's right. Yeah, so this is related to the question number 5, so please raise. So I'm still talking about question number 2, okay? So there are many questions actually. But so let me, actually it is a good idea to give a more intuitive understanding of this operator. So first of all, so that's why I first started with the definition of Vezina products. So so this string is mapped to this vertical line, and this string is mapped to this vertical line. So it is, we can think of this as a kind of like gluing this string and this string. So this is how we understand the Vezina product. Then the star product, as you often see, that so the 3 strings are mapped to, okay, this region, this line, and then this one and this one. So it is written like this kind of overlap, right? So as I mentioned, this gauge invariant operator is kind of like gluing the left half of the string and the right half of the string, okay? And then we put a gauge invariant operator at the midpoint. So let me write it upside down, so it's going to be like this. Is it clear? Yes. So, okay, this is the definition of the gauge invariant operator. So this is the most important slide in my talk. So even if you are sleepy, and don't miss it. So these gauge invariant operators actually have an interesting origin in open cross-string field theory. So one parameter family of formulation of open bosonic string field theory were constructed by Burton Seibach in 1992, and it was observed that in a singular limit, the action reduces to that of this cubic theory with additional vertex which coupled one off-shell open string field and one on-shell cross-string field. So actually, I mentioned in the introduction that the action for the cross-string field theory is very complicated, and the open cross-string field theory is much more complicated. I don't even want to try to write it here, but it is amazing. In this singular limit, the whole action reduces to just 3 terms. Okay. Okay, now this is the action I already explained, the open string field theory, is the cubic interaction. And then this is, okay, I wrote it in the WP's product in the open string channel. So it is phi is a cross-string field, and V phi is a map from a cross-string field to open string field. Yeah, actually it is, so otherwise it is not very inconsistent. So that's actually it is, and also you will see that the gauge invariance requires this to be on shell. Across. Yes, linear as yes, EQB in the crossing channel. So that may be related to. Sorry? Yeah, I'm gonna explain it. Yeah, it's a very important point. Okay, so so this is okay. So the kinetic actually, so it is very strange limit. Okay, so we studied the open cross-string field theory, but the kinetic term of the cross-string field theory is gone. It's absent. So actually, this is no longer open cross-string field theory. It is open string field theory, and then this on-shell coupling. So this term. So in the context, so as an open string field theory, this is kind of like this is actually a source term for the this gauge invariant operators. So if you expand this off-shell, on-shell cross-string field in components field, so this can be regarded as the source term for this. Yeah.
Open string field.
That's right. So when you write it that way, so it is like, okay. So if you expand cross-string field as a state times component field, okay, then if you use a state operator correspondence, then this, so the component field of the cross-string field times something. That something is precisely the same as this operator. That's a statement. So this is very interesting. And then, so an important consequence from this relation of the gauge invariant operators and open cross-string field theory is that Feynman diagrams of a correlation function of these gauge invariant operators are given by Riemann surfaces containing holes with bulk punctures, and the modular space of such Riemann surfaces is covered. So let me illustrate how the modular space of disks with 2 bulk punctures is covered in the singular limit. So disks with 2 cross-link punctures, bulk punctures. So I use this, present disk, okay, maybe it is consistent to write the boundary in blue, maybe. It is slightly consistent, but you may not distinguish the color, but anyway. So this is the disk. I use disk as the unit disk. And one of the cross-link vertex operators can be brought to the origin, right? Then the second vertex operator can be brought to this segment, right? So by rotational symmetry. So it is somewhere around here. So the modular space of disks with 2 bulk punctures, this is given by this segment. And before taking this singular limit, let me explain how this modular space is covered by open cross-link field theory. So there are 2 Feynman diagrams. The first one is the cross-links becomes open string. I tried to write this figure yesterday, so I hope I can write it slightly better. So this is at the boundary. So I wanted to have a yellow chalk, but anyways. So this is the open string, sorry, this is cross string, and this is cross string because of open string. This is the vertex, open cross vertex. So we have one more. And then I'm gonna contract with open string propagators. Okay, so. So this has a disk with two crossing states. Okay, and then in the limit of very long open string propagator, so this corresponds to the this region of the modular space. This is the open string degeneration. Okay, so this Feynman diagrams covered some part of the modular space here to somewhere, and there are another Feynman diagrams which consists of a cubic vertex of cross strings, and then this is a one-point vertex of a cross string on a disk. So this is a disk boundary, and this is one. Actually, the open cross string field theory require this kind of a little bit funny vertex, and then we can contract these two vertices by cross string propagator. Okay, so we have this is a disk with two crossing states, and in the limit of very long cross string propagator, this corresponds to the this region of the modular space. So these Feynman diagrams cover the region. So the gauge invariance of open cross string field theory is it's related to the covering of this modular space. So these two diagrams cover the whole modular space. This is how the modular space is covered in open cross string field theory before taking the singular limit. Now consider the how this works after the singular limit. So after the singular limit, so we have a vertex given by this. So we have this. Then we have another vertex. So then I'm gonna contract this with a propagator. So do you have a propagator? No? Actually, I have one here. I found it in the printer room. So this is an open string propagator, right? So I'm going to use this to contract these two vertices. So I hold it. And then, okay. So this one is glued, this one is glued. So I'm going to glue this and here. Then I'm going to have a, I hope I can do that. So now we have a disk, right? And then we have a crossing vertex operator here and here. Do you have a picture? Okay. So this is a disk with a vertex operator here and here. And in the limit of very long open string propagation, it covers this region as before. But now consider the limit of the other limit, vanishing open string channel propagator. So in that case, these two crossing propagator collide. So which means these diagrams cover these Feynman diagrams cover all the way to here. Okay, so without contribution from these diagrams, the whole diagram is covered by this vertex and the open string propagator. So this is one example of how this this singular limit of the open cross string field theory covers the modular space. So as you may find that this picture, open bosonic string field theory with this particular cubic vertex and this particular vertex of an open cross vertex is distinguished role in this context. So as a classical theory, we can have many formulation of open bosonic string field theory. They are related by field definition. But this context, this seems to be very special. So let us now consider the theory on n-coincident d-branes. If we evaluate correlation function of these gauge invariant operators in the 1/n expansion, by construction, it reproduces the crossing perturbation theory with hold in the worldsheet, as mentioned before. So the question number 2 was, what quantity should we consider in open string field theory? My answer is that we should consider correlation function of the gauge invariant operators. They can be evaluated in the 1/n expansion in terms of Feynman diagrams of cross-link field theory with holes in the worldsheet. So by the way, so this is the open string field theory. So we can also consider the dynamics of open strings in addition to the correlation functions of the gauge invariant operators. So this may be related to the discussion of the non-singlet sector in the matrix model by Vezina. And I think it is interesting, but then in the rest of my talk, I will concentrate on the correlation function of the gauge invariant operators. So far, so good, okay? However, actually, Riemann surfaces associated with such Feynman diagrams contain at least one hole, okay, by construction. And contributions from Riemann surfaces without holes are missing. So in the context of on-shear scattering amplitudes, so these Feynman diagrams are necessary for factorization. So question number 3. So what do we lose in the missing Feynman diagrams? So let us again recall the explanation of the ADS-32 correspondence. Okay. So I explained that. So there are 2 descriptions. One is D-branes, and the other one is with the 3-brane solution of supergravity. And then in both descriptions, there are 2 decoupled sectors in the low energy limit, as I wrote before. The one of them is a free theory in 10 dimensions from the Crosslearning sector. And we identify the 2D expression of the other sector. That's we arrived at the conjecture. And in the low energy limit, the missing contributions from a Feynman diagram without holes in the worldsheet correspond to those of the free theory, right? So in the low energy limit, the contribution from open string field theory are exactly what we want. So the answer to question number 3, what do we lose in the missing Feynman diagrams? My answer is nothing in the low energy limit. So previously, there were some attempts to reproduce Crosslearning theory without holes in the worldsheet from the correlation function of these gauge invariant operators, for example, in the context of Tachyon condensation. I think it will be very interesting, but I would emphasize that my approach is different. Okay? So I'm not trying to reproduce Crosslearning theory on the original background, on the flat spacetime. And but this is the difference. And also, after taking the low energy limit, the quantities we are considering are non-logan on-shear scattering amplitudes as used. So it is also the insight we learned from ADS-32 correspondence. It is more like Witten diagrams in the bulk. So there may be a physical interpretation about this correlation function of the gauge invariant operators before taking the limit, low energy limit, but I have not figured it out. So in the low energy limit, okay, I'm going to make a few more comments. On the one comment is that in the low energy limit, the on-shear condition for massive state is no longer satisfied. But I would emphasize that there are massive states in the flat spacetime in 10 dimensions with D-branes. And the massive state in the, actually I already erased the figure, but massive state, Crosslearning state in the ADS5 crosses 5 arises from the massive sector in the flat spacetime. So if we are assuming the equivalence of this Crosslearning field theory with holes in the worldsheet and Crosslearning theory on the curved background, then 1/by expansion of the correlation function of the gauge invariant operators should incorporate interaction in terms of a massive Crosslearning state in this curved background. To summarize, I would claim that the correlation function of gauge invariant operators, evaluation of this correlation function in the 1/n expansion can be interpreted as a Crosslearning perturbation theory in the low energy limit. So, if open string field theory for finite n is consistent quantum theory, it provides a non-perturbative definition of the Crosslearning theory. If we evaluate the 1/n, it is going to be a Crosslearning theory. If it is defined for finite n, it is a non-perturbative definition. after taking the low energy limit. So that's the important point. So I say something about this. So I expect there might be some interpretation before taking the limit, but I have not figured it out. So if you have an by low energy limit, so it is so by low energy limit. So this is a coupling. This is a source term for the gauge invariant operators. Gauge invariant operators are labeled by momentum. So by low energy limit, I'm interested in the gauge invariant operator with low momentum, which is much lower than the scale determined alpha prime. If we concentrate on this, before, yes. But that is so that's what I learned from your review. So okay.
How about open? So are you going to be using this? Can also be used to calculate S matrices.
Yeah, that's also mentioned this.
Do you allow open string state to be with high momentum?
Yeah, you can consider that, but I don't have any physical interpretation. So yeah, that
When you talk about the low energy, do you allow yourself to calculate high energy scattering of open string in the background of low energy crossing?
So in this context, it is not interesting quantity we are looking at. But I think in principle.
So you're saying that I thought that your claim is that this theory with crossing are just on shared background.
Yeah,
And open string just integrate over.
that's right. Yeah, yes.
Makes sense and generate all the necessary diagrams, modular space.
Yes. For correlation function of the gauge invariant operator.
Which situation? So in the case when you can calculate open string scattering with arbitrary high energy for open string,
So
provided cross strings are in low energy.
So that's in this talk, I'm not considering the external state to be on-share open string state. It is. I think it is possible that it may be related to the discussion of the Maldasena's long for this open string, but I'm not quite sure.
So here you are only considering
Correlation function of
closed string which are in low energy.
yeah, that's like in the n equal 4 super pi maze. You can also consider the scattering amplitude in n equal 4 super pi maze, maybe if. But then in the context of additivity correspondence, we are considering the correlation function of single trace operators. That's the analogous situation. Yes. So I'm interested. Okay. No. But then, so I'm interested in the low energy limit. So I expect that in the low energy limit, it's going to be n equal 4 super pi maze. So I'm gonna comment on the yeah. That's I expect. Yeah. That's okay. So if I so where are we? So there's I think I explained this. So I think I'm going to be question number 4. Is open string field theory a consistent quantum theory? So I don't expect the open string field theory in general to be a consistent quantum theory. But it is interesting to consider in the context of topological strings. For example, the Chern-Simon three-dimensional Chern-Simon gauge theory can be formulated as an open string field theory. So in that case, in that context, this might be a complete quantum theory. Also, it is interesting to consider Konchevich model in this context, as discussed by Gayotto last theory. If you consider FZZT branes, and then actually they claim that it is equivalent to the Konchevich model. But then, so they introduce some observables, but it might be derived in this approach. So that's what I'm interested in. But anyway, but in general, I don't think open bosonic string field theory would be a consistent quantum theory. On the other hand, open superstring field theory can be a consistent quantum theory. But then when we quantize open superstring field theory, we know that both the Neveu-Short sector and the Ramond sectors are necessary for consistency in such a quantum treatment. Okay? So, and then actually the action of construction of the action, action of open superstring field theory involving the Ramond sector had not been constructed for many years, but this problem was solved recently. So now I think we have now several formulations of open superstring field theory which are complete at the classical level. But I would still think that the formulation of open superstring field theory needs to be developed further. And it is an important question to address whether or not open superstring field theory is consistent as a quantum theory. But at the same time, I think we are in a position to discuss how we should use this open superstring field theory to understand the mechanism which realizes the ADS-50 correspondence and so on. So this is one of the main messages of this talk. By the way, this may be also interesting, maybe some insight into this formulation of this open superstring field theory. So as I said, in the case of open bosonic string field theory, there are many classical theory which are equivalent by field definition, but on this particular star product is the theory with star product and gauge invariant observer somehow plays a distinguished role. So there might be something analogous happened in the open superstring field theory. So it's the question number 4 was is open superstring field theory open string field theory a consistent quantum theory? And my answer is that the open string field theory for the topological string or the non-critical string can be a consistent quantum theory. And open superstring theory can also be a consistent quantum theory, which motivates us to extend our discussion to the superstring. Okay, here is the final question, number 5. So can we make sense of the path integral of open string fields? Okay. So as I mentioned before, I don't think the path integral of the cross-string field theory to be promising for a non-perturbative definition of cross-string theory. On the other hand, there will be a better chance of making sense of the path integral of open string field theory. However, it may still be difficult because the open string field contains infinitely many component fields. So therefore, let us consider integrating out the massive fields to obtain a theory in terms of the massless field, which is actually discussed in the context of cross-string field theory by Ashok Sen in the Wilsonian, so it is called the Wilsonian approach, Wilsonian effective action for the string field theory. So, okay, the resulting theory for the massless field will be complicated. But we can show that if the original theory has the structure called infinity, I don't have time to explain this important structure, but if the original action has an infinity structure, after integrated out, the resulting theory contains an infinity structure. That was one of the very important results of this paper. This infinity structure severely constrains the form of the interactions. The cubic interaction can be written explicitly, and the interaction terms, which are higher than the cubic, might be determined by this infinity structure, including alpha prime corrections. So, if there are, but after integrating out the massive fields, there are only a finite number of fields. So the path integral of those fields can be defined in the same way as in ordinary quantum field theory. So, also, of course, we also need to include the source term for the gauge invariant operator, which is related to your question before. So, in the process of integrating out massive fields, the coupling of the cross-string and the multiple open string fields are generated. And the gauge invariant operator, in terms of the massless field, will resemble single trace operator in the UN gauge theories in the low energy limit. Also, in the process, we have to throw away Feynman diagrams involving only propagator for the massive fields to obtain action for the massless field. But I don't expect this Feynman diagram to give a non-vanishing contribution in the low energy limit. But we may have to be a bit more careful, but I'm optimistic about this. So the solution, so the answer to the question number 5. So can we make sense of the path integral of open string field series? My answer is that we can integrate out massive fields. The path integral of a finite number of massive fields can be defined in the same way as in the ordinary quantum field theory. So in the case of these three branes, the resulting theory will be equivalent to n equal 4 super ion modes in the low energy limit. That's I expected. So, but in our approach, we keep track of the relation to the crossing theory with Horde in the worldsheet. So this can be useful in proving the ADS50 correspondence. So as we mentioned before, the worldsheet picture can be seen in each order in the expansion of the Hooft coupling constant. And then in the hexagon approach, based on the integrability by Basso, Komatsu, and Vieira, I was very curious, but because then in the worldsheet picture seems to appear even in the weak coupling region. But our approach might provide explanation for this feature. And then I believe there are several advantages in this approach. So first, we define correlation function of the gauge operators before taking the low energy limit. So this can provide a well-defined setting to discuss the correspondence after taking the limit, such as the usual ADS50 dictionary between correlation function on the boundary and the supergravity calculation in the bulk, which might be difficult. But then this can provide a well-defined setting for discuss this limit. Second, we have a relation between gauge invariant operators and the crossing state from the beginning. So this can be an advantage. So although it might be difficult to keep track of the relation after taking the limit. So we don't need, okay. Third, our discussion can be applied to any background by taking appropriate decoupling limit, which was discussed by Douglas Cabot, Puryashenko, DKPS limit a long time ago. In particular, our discussion doesn't directly rely on conformal symmetry or supersymmetry. So let me summarize my talk. Okay, actually it is very easy to summarize because I just repeat the question and answers. Okay, question number 1, what kind of crossing theory we should consider? My answer was, we should consider crossing theory with holes in the worldsheet. Question number 2, what quantities should we consider in open string field theory? We should consider correlation function of the gauge invariant operators. This can be evaluated in the 1-over expansion in terms of Feynman diagrams of crossing theory with holes in the worldsheet, as I mentioned. And there are missing Feynman diagrams, but what do we lose in the missing Feynman diagrams? Nothing in the low energy limit. Is open string field theory a consistent quantum theory? Open string field theory for topological string or the non-critical string can be a consistent quantum theory. The open superstring field theory can also be a consistent quantum theory, which is interesting. So this motivates us to extend the discussion to the superstring. Then can we make sense of the path integral? Then we can integrate at the massive fields. The path integral of the massive fields can be defined in the same way as in ordinary quantum field theory. So I presented a roadmap I have in mind. So I hope you enjoy it. So Noi Shamo Kui. So we are here. Is it correct? Okay, we are here. So the title of my talk is that the non-perturbative definition of crossing via open string field theory. So let's take via string field theory to get to the ADS correspondence. Thank you. You mean crossing background or open? So it can be in principle anything. So that's I emphasize. So our discussion can be applied to any background. I only assume so that the coupling of the open string and cross string in a particular limit. Yeah.
So there are two different closed string backgrounds.
Yes. Yeah, I think I explained this before. Okay. Okay. We started with flat space, 10-dimensional space-time with D branes. And then this can be explained in the, so this is a 3-brane background, okay? ADS5 cross S5 is the region of this region after taking the near horizon limit. This is the correspondence, okay?
You said you can do things more general.
Yeah, you don't have to start with this particular setup. You don't have to start with the D3 branes. You can have a more general background.
Can you see something like ADS5 versus 5 arising from your discussion?
So we don't know. So actually, that is the issue. I said I don't. So in this talk, so there are only halfway to the proving the ADS relative correspondence. The other important halfway is the discussion like this. Okay. So in this talk, I was concentrated on to reproduce a cross-linking field theory with holding the worldsheet, which is so it is okay. In general, I don't know. This theory is equivalent to some. So it is likely to contain gravity. That's basically I'm interested in. But then this can if you start with a more general D-brane configuration, I don't. So I think we can do the same thing up to here. But then equivalent. So this may be equivalent to some. Okay, it is a cross-linking field theory without holes in a curved background. But I don't know what kind of curved background in general. So maybe Hiroshi will prove very soon. Okay.
So this cross-string Feynman diagrams with holes.
Uh-huh.
So holes are boundary.
Yeah.
Right? And therefore they are classified by boundary conditions. So,
That's right. Yeah.
so if you start with open string field theory
Uh-huh.
on some different system, let's say on ND3 branes,
Yeah.
it seems namely it seems that you only get Feynman diagrams with the boundary condition of the starting background.
That's right. Yeah.
But I guess that to define perturbatively, I mean, in the recipe of getting this clustering amplitude, you have to sum over all possible boundary conditions that this whole has, right? Because you have to, you have to consider all possible branes. And so I was wondering how this can be achieved.
Actually, I don't know about this, but then I'm interested in the quantum treatment of the open string field theory. For finite coupling, this picture, like D-brane, so there's some background with some particular boundary condition will be lost for finite coupling, finite coupling. So, but I'm not sure. So I need to integrate over the open string fields. So that may partially incorporate some information about the other background, but it is not very explicit in this.
Yeah, but this may be a very highly quantum effect in open strings because there is some other open string, but integral will have to go to the all possible saddle points in the
Yeah.
And therefore, maybe it is only achievable really being able to explicitly do the open string of integral.
Yeah. But you can ask the same question for the n equals 4 super ms, right? Yeah.